So the last page is finding the area of a segment of a circle, and that is the region that's bounded by an arc and its chord. So if we've got the arc here and this chord here, that little region in there is going to be the segment of a circle. If the arc is a minor arc, then the area of the segment can be found by subtracting the area of the triangle from the area of the sector ODFE, which would be ODFE. So taking that area and subtracting out the triangle, and all you're left with is the segment of the circle. So again, that'll only work with minor arcs, which are less than half the circle. If you go over half the circle, then you have to be a little bit more creative with your solution. Okay. Before we do that, I guess let's just remind you that the area of a sector is equal to 1/2 the radius squared times theta. Remember where that's in radians. And that will give you the entire area. Okay. So in this example, it says a sector has a central angle of 150 degrees. So that is a minor arc. It's less than 180 or less than half the circle. In a circle with a radius of 1.5 inches. Find the area of the circular segment to the nearest tenth. Okay. So if we get this sketch drawn out, we've got about 150 degrees here. And we are finding this area. We want to find the area of the segment. Okay. So because that formula has the central angle given to us in radians as opposed to degrees, we know that it's 150 degrees, so that would be 150 times pi over 180, or this one should be one that you've got pretty close to memorized, of 5 pi over 6. So we'll have to use the radian measure for theta of 5 pi over 6 as opposed to the 150 degrees. Okay. So now we can use this idea that the area of a segment, or the area of the segment, so what I have right now highlighted in red, is going to be area of the sector minus the area of the triangle. So again, we'll find the area of the entire sector and subtract out the area of the triangle, and all we'll be left with is this piece right here, this segment of what's left over. Okay. So the area of the sector is the formula that I reminded you of up top, which is 1/2 times the radius squared times theta, and we are going to subtract the area of the triangle. So let's take a closer look at this triangle that we've got, or that I just erased. I know that that's going to be 150 degrees. And I can label this other side as 11.5 because it's a circle. I know that any radius drawn from the center is going to have to be congruent to any other radius in the same circle. So that's the case where I've got two side lengths and the included angle. So if you look back to the page before where we talked about the different formulas, we're going to want to use that top formula where we know two sides and the included angle. So that formula was 1/2 AB times the sine of the included angle. So that's what we'll plug in here. So we're going to subtract 1/2 AB times the sine of our included angle. Okay. Now we just get to start plugging things in where they belong. So we will take 1/2 for radius squared would be 11.5 squared times theta, which we determined was 5 pi over 6. And we are going to subtract 1/2 AB. Those are our two sides. So when we look at this, it's going to be A b, so I know it's going to be 11.5 times 11.5. So I would rather type that in as 11.5 squared. Plus, then you can already see some similarities between the first set of parentheses and the second. And now we have to multiply this by the sine of c, or our included angle, which is the 5 pi over 6, or 150 degrees. But because we want to make sure our calculator is set to the right mode, we want to have the same mode for both parts of the problem. Okay. There are a couple of similarities, I said, between this first set of parentheses and the second set, so we could factor that out. But you don't have to factor it out if you're solving. I just kind of want to show you a simplified version of the formula if you're going to do this again. So we can say it's we can factor out a 1/2 times 11.5 squared. Oops, I didn't need that parentheses. 1/2 times 11.5 squared from both, and now what I'm left with in the first parenthesis is just 5 pi over 6 minus, and now I already factored that out here, so then all I'm left with is the sine of 5 pi over 6. So if you have to do other problems like this in the future, this is the area of a segment, which you could simplify and say, well, that's just 1/2 radius squared times this 5 pi over 6 was our angle theta, and we're subtracting the sine of whatever that angle theta was. So if you have to do more problems or you're finding the area of a segment, you could just jump right ahead to this formula here. So maybe put a box around that one, but we can just keep working from above and kind of hop over that and just keep working. So now we're just plugging these in. We've got our 1/2 times 11.5 squared times 5 pi over 6, and we're subtracting this. So now I'm looking back up here. We're subtracting sine of 5 pi over 6, and you could do a calculation on your calculator to figure out, well, what is the sine of 5 pi over 6? Hopefully that's one that you can reference quickly in your brain. The reference angle for that would be a 30-degree angle, or pi over 6, and so the sine of that is going to be 1/2. And now it's just a matter of typing that in. We've got 66.125 times about 2.118, and so that's approximate. I'd say it'd be better to leave that exact on your calculator until you're going to do your final rounding, which is about 140.05, and I have to look back at the directions because it said round to the nearest tenth. So 140.05 would round to about 140.1, and I think that was centimeters, nope, inches. So it's inches squared. So the area of that segment would be 140.1 inches squared approximately.